it is a truth not so universally known. As chips got smarter, computers got hotter. And keeping them cool? That became one of the most underrated yet most fascinating arms races in tech history. This is the story of how computer cooling evolved, from the noisy hum of vacuum tubes in the 1940s to silent tanks of synthetic oil in the AI era. Let's go back to where it all began. The ENIAC, one of the first general-purpose digital computers, was built during World War II and unveiled in 1945. It was massive, 30 tons of machinery filled with 17,000 vacuum tubes consuming 150 kilowatts of power. But those vacuum tubes, they ran hot, and not warm laptop hot. We're talking 110 space heaters kind of hot. To prevent constant burnout, engineers installed powerful blowers and early air conditioning right inside the computer room. Even so, temperatures reached a blistering 49 digs, 120 digs. When ENIAC was relocated from Philadelphia to an army site in Maryland, poor airflow led to frequent tube failures, a nightmare for operators. By 1948, IBM released the 604 Calculating Punch, a punch card computer using 1,400 vacuum tubes. To simplify maintenance, they invented the pluggable unit, small tube modules bundled with capacitors and resistors. Easy to replace? Yes, but compact design meant higher thermal density. So IBM added fans and filters, and cooling became a core engineering constraint. Also in 1948, Bell Labs introduced a breakthrough, the transistor. Newspapers hailed it as a non-heating device. The New York Times even claimed it wouldn't generate heat like vacuum tubes. Early hope was maybe the heat problem is over. But the truth? That dream lasted less than a decade. With the invention of the integrated circuit in 1958, transistors could be packed tighter than ever. But this density brought new thermal problems. By the 1960s, computers went from a few hundred transistors to tens of thousands. And with every leap in computing power came more heat. Cooling vacuum tubes with liquid wasn't new. In fact, back in 1935, engineer I.E. Muromtsev experimented with water-based cooling for high-power tubes. By the 1950s, as military systems needed power-hungry analog signals, liquid cooling returned. This time for defense projects. Air wasn't efficient enough anymore. Water has 1,000 to 3,500 times the heat capacity of air. But water and electronics don't mix. So companies like 3M and DuPont developed specialized fluids like Fluorinert and Freon, safe for electronics, even if terrible for the environment. In 1964, IBM released its legendary System 360 mainframe series. Its most powerful version, the Model 91, broke ground with hybrid cooling, mixing air and water. It introduced air-water heat exchangers between circuit boards. This brought down internal air temperature rises from 29 degrees to 7 degrees, a game changer. By 1968, IBM added a dual-loop water system. Inner loop purified water, outer loop building water. This innovation, the coolant distribution unit, remains standard in modern data centers. In 1977, Honeywell took it a step further with their Model 6685, marketing true liquid cooling. While the term was a bit misleading, the liquid never actually touched the chips. They brought cooling directly to the chip package via a cold plate and hose. The setup was so efficient and silent, Honeywell engineers could pack logic chips tighter than ever before. IBM developed multi-chip modules, MCMs, in the late 70s, multiple dies packed into a single substrate, now known as chiplets. But more chips meant more heat. To solve this, IBM engineers invented the thermal conduction module, TCM, a clever piston and helium chamber design that maximized contact with the cold plate. Later they switched to thermal paste for simplicity. These systems could dissipate 64 watts per square centimeter, insane for that era. With the rise of very large-scale integration, VLSI, in the 1980s, chip designs moved from thousands to hundreds of thousands of components per die. Surface temperatures soared to 50 to 100 degrees, raising fears of reaching a thermal barrier. Some extrapolated future chips would match the heat flux of the sun's surface. Enter CMOS. Although invented in 1962 by Frank Wanless and Tom Saar, CMOS, complementary metal oxide semiconductor, gained traction in the 1980s for one reason: low power draw. In 1980, Hitachi released the first CMOS DRAM. In 1982, Intel joined the party. In 1985, the Intel 386 CPU went CMOS. And in 1987, CMOS chip sales surpassed NMOS. CMOS chips consumed up to 20 degrees less heat than NMOS, which bought engineers precious breathing room. But not everyone made the switch. Seymour Cray, the father of supercomputers, wasn't satisfied. His Cray 2, released in 1985, used emitter-coupled logic, ECL, ultra-fast, ultra-hot bipolar chips. And Cray wanted them tight, wires no longer than 16 inches. To cool this silicon sandwich, Cray engineers did something radical. They built a circular tank, stacked 336 modules, and filled it with Fluorinert liquid. Not beside the chips over them. Yes, Cray 2 used full immersion cooling. They pumped 70 gallons per minute, letting the coolant flow like a waterfall over multi-million-dollar circuits. And yes, it worked. Cray would later joke, "I started as a computer scientist, became an engineer, and now I'm a plumber." By 1993, even IBM gave up on exotic logic families like ECL and fully embraced CMOS. Why? Because CMOS chips were powerful enough and cheap to cool. You could use fans, heat sinks, or basic cold plates. Suddenly, liquid cooling looked unnecessary for most systems. Since the 1970s, Moore's law and Dennard scaling worked hand in hand. Smaller transistors equaled lower power plus faster speeds. But by 2004, it broke. At 90 nm, the transistor gate became too thin, and leakage currents meant that even off transistors kept consuming power. The result? More heat, no matter how small the transistor. Intel and AMD pivoted to multi-core designs just to survive. In 2008, IBM launched the Power 575 server node, featuring cold plate water cooling. It absorbed 80% of chip heat and reduced data center energy consumption by 40%. IBM called it a back-to-the-future moment. Soon after, ETH Zurich and IBM created Aquasar, a hot water-cooled supercomputer that reused waste heat to warm buildings. Japan's Tokyo Tech University introduced the Tsubame KFC in the early 2010s. This supercomputer dunked CPUs and GPUs in a low-viscosity synthetic oil. Fans and moving parts were removed. The result? Quiet operation, power usage efficiency, 1.294.5 gigaflops per watt. And yes, it was gently dipped in tempura batter first. Not literally, but the engineers had fun with the metaphor. By 2020, consumer CPUs like Intel's 10th gen chips generated 125 watts under full load. But that was nothing. NVIDIA's H100 AI Accelerator 2022 pushed 700 watts. Its successor, the B200, hit 1,000 watts. Suddenly, fans weren't enough. In Singapore, a startup called Firmus Technologies developed a single-phase immersion system, similar to Tsubame KFC, but for AI data centers. Their setup? No fans, no moving parts. Silent, surreal, sci-fi ambience, up to 60% lower energy costs. Inside, $30,000. NVIDIA GPUs lie fully submerged in a clear synthetic oil, chilling under lights like submerged treasures. Semi-analysis projects that NVIDIA's upcoming 3nm Rubin AI chips, due in 2026, could emit 1,800 watts of heat per chip. That's not just hot, that's starter fire hot. To deal with it, experts are exploring direct-to-chip cold plates, microfluidic cooling, two-phase immersion systems. But here's the twist. Every time we solve the heat problem, we just build something hotter. From vacuum tubes to Cray aquariums, from CMOS revolutions to submerged AI servers, one thing's clear. Computing gets faster, cooling gets smarter, and the cycle repeats. Because in tech, every breakthrough ends with a blueprint for more heat.